Hi, everyone. My name's Jeremy. Quick kind of background on me. I was a physicist a long, long time ago, a lifetime ago. And then I started doing a bunch of startup stuff, doing tech stuff. Anyway, one of the things I did when I was a physicist is I worked a lot on quantum mechanics. And quantum mechanics is this really, really weird thing because it's the set of rules that the universe actually uses to decide what to make everything in the universe do next. So if you're wondering, how is it that computers work? How is it that light bulbs can turn on? Why is it that like a baseball hits a racket in a certain way? The real answer to those questions is hidden in quantum mechanics. The laws of quantum mechanics are actually really, really counterintuitive. They're surprising. There's all kinds of weird stuff that happens when you look at quantum mechanics close up. And what I want to do today is show you guys one of the most amazing things quantum mechanics tells us about the universe. And that is that there's a good possibility, I would say a strong likelihood, that parallel universes exist. And I want to explain, I'll do my best, and please feel free to interrupt me with questions. I want to explain to you guys why it is that people think parallel universes are a thing. And this is going to involve just a little bit of quick background, but it actually isn't, I don't think it's that hard to get across kind of the core reason why people think this is the case. But to do that, I'm just going to, so I've got this little whiteboard thing. I hope you guys can see that. Yes. Great, because I was planning on using that a fair bit. Good. So what I want to do is just start with introducing a kind of particle, a kind of thing that exists in the universe. And you guys might know about atoms. You might have heard of atoms. Basically, if you zoom in on something, if you zoom in on almost anything close enough, you'll realize that it's actually made of these tiny little particles, these little kind of almost ball-like things that are called atoms. And atoms are made of stuff too. So there are subparts of atoms. And one of those subparts is called an electron. And hopefully I can write reasonably legibly there. Anyway, it's called an electron. Okay, good. So there's a part of an atom that's called an electron. It's basically like a tiny little ball. So imagine this like little ball. And one thing we know about balls is that they can spin. So imagine like a tennis ball, right? You can spin a tennis ball clockwise. You can spin it counterclockwise. You can spin it in two little directions. So here's our little electron, and it can spin counterclockwise, which I think is what that is, or it can spin clockwise. So nothing too exciting here. Really seems like the universe is pretty boring when I paint this picture. One of the really weird things about quantum mechanics is that these particles, these electrons, can actually spin not just clockwise or counterclockwise, but in both directions at the same time. So this is the single most insane thing about quantum mechanics. It's probably the only weird thing about it. Once you can wrap your mind around that, if you can get yourself to accept that, then you've kind of grappled with the core of quantum mechanics here. So the main weird thing about quantum mechanics is that these electrons, these tiny little balls, can spin clockwise or counterclockwise, and they also can do both at the same time. So the best way to think about this, I mean, our minds, right? If I tell you that, you're kind of going to go, wait, that doesn't really make any sense. I've never seen that happen. That, by the way, is one of the biggest mysteries in quantum mechanics. If it's true that things like electrons can spin in two directions at the same time, how come we've never seen that happen in the real world? And so that's the first little tiny hint that there's something really, really weird and possibly very, very wrong about the picture of the universe that we have. The universe isn't actually what we think it is. And this is the first place where we get a little hint of that. Okay, so with that quick primer, I just want to give you another way of thinking about this. So if you think about an electron spinning clockwise, if that's like the color white, and an electron spinning counterclockwise, and that's like the color black, then what I'm saying here is that electrons can be a shade of gray. They can be in between. They can spin like counterclockwise and clockwise at the same time, a little bit more clockwise than counterclockwise. It's like this weird mix. They're really doing both things at the same time. Okay. I almost want to hesitate to ask if you guys have any questions at this point, because this is already so counterintuitive. But in a way, it's kind of something we just have to learn to accept at this point. But if you guys have a question about this, let me know. You don't have to. There's no pressure. All right. Cool, cool, cool. Okay, so let's talk about how physicists with big round glasses and very white, thick lab coats solve real problems. So here is what physicists do all day. They draw pictures. So I want to introduce you to a stick figure that we will call Steve. Okay, here's the thing. Physicists solve all their problems using pictures. There's nothing more complicated to physics than drawing pictures. There's nothing more complicated to quantum mechanics than drawing pictures. It's just that physicists don't want you to know that. Physicists only get paid if people think that what they're doing is super complicated, and so they try to make it seem complicated by hiding their pictures in little boxes called kets. So what we're going to do is we've got a little stick figure here called Steve, and I'm going to do this. I'm going to draw a little weird box with like a straight line and like an angled bracket. And this thing, this is called a ket. And a ket is not useful for anything really other than making people think that you're doing something more complicated than you actually are. So really you're drawing pictures, but by putting something in a ket, what you're telling people is, oh, I'm no longer talking about Steve. I'm talking about the quantum, boy, it's hard to write with a mouse. The quantum state of Steve. So I'm talking about the quantum state of Steve. In other words, I'm going to pretend that Steve is a quantum mechanical thing, that Steve follows the laws of quantum mechanics. And that's all I'm doing by putting Steve inside this ket. So again, just a cheap trick for physicists to make themselves feel better, because now it looks like we're doing something more complicated than we are, but we're really just drawing pictures. Okay, so why is Jeremie bothering to tell us all about kets and all about Steve? Well, remember how I told you that electrons can spin in a certain direction? Let's say this is an electron spinning, I don't know what that is, counterclockwise, let's say, okay? So this is an electron spinning counterclockwise. This is the quantum state of an electron spinning counterclockwise. So now look at that. We went from doing doodles to doing physics just by drawing that little angled bracket, right? So that's all that means. That's a quantum state of an electron spinning clockwise. Here is the quantum state of an electron spinning in the other direction. Okay. Now I told you that electrons can spin clockwise. They can spin counterclockwise. They can also do both at the same time. This plus sign is what physicists use to say that the electron is doing this thing and this thing at the same time. Okay? So the plus sign is this magical thing that says, oh, this thing has like, I don't know, it's all mixed up. It's doing these two things at the same time. If you ask me which direction is this electron spinning in, I will have no choice but to answer your question by saying, I have absolutely no idea. It's kind of doing both. It's not doing one or the other. It really is doing both things at the same time. Can't emphasize that enough. So that's what that plus sign means. Does that make, I was going to say, does that make sense? None of this makes any sense, but does that kind of, sort of, pseudo make sense?
Yeah.
Maybe. Okay, sweet.
Yeah, it makes sense.
Excellent. All right. Glad you're on board so far. A bit. Okay, a bit is, I think a bit is like the sweet spot here. If you get this a bit, then you're doing perfectly well. Okay, so we have our electron. It's like weirdly doing this thing, and it's doing this thing at the same time. The way we show that is by using this plus sign. Okay. Now, one last thing I have to show you before I can prove to you that you live in a parallel universe. I'm going to have to show you how to tell stories with these little ket things. So here's what we're going to imagine. We have our electron, and I don't know, let's say it's spinning this way. And next to this electron, we're going to put a magical little detector. So this thing kind of, I don't know, scans the electron. And it's going to tell whether the electron is spinning clockwise or counterclockwise. Okay? So this is a magic detector. What it does is it detects the spin direction of the electron. That's all it does. It's its only purpose in life. And if the electron, let's say, is spinning clockwise, so it's spinning in one particular direction, this detector will send a signal to, and this is where things get a little bit gruesome, a gun. Uh-oh. And that gun, if the detector goes click, and the detector again will go click only if the electron's spinning clockwise, that gun, unfortunately, is pointed to a cat. Okay, so hopefully no one here has any cats. If you do, this is all imaginary. So no one's ever run this experiment, but they could imagine doing it. And this is exactly what physicists did in like, I don't know, 1920 something. So a bunch of physicists, in one particular called Schrödinger, you don't need to worry about how to pronounce his name or how to spell it, but basically he imagined setting up this very gruesome experiment. He put an electron, something like an electron, in a box, and there was this detector that would go click if the electron was spinning clockwise. If it was spinning the other way, the detector wouldn't do anything. And if it went click, it would send this signal to this gun that would fire its bullet and knock out our little cat here, okay? So all of this is inside a box. We're gonna put this inside a box just like that. Okay. Why is Jeremie telling me a story about a cat in a box? Okay, let's find out. So the first thing I wanna do is let's draw out what happens in this story using our cats, okay? So we're gonna imagine, let's take our electron, and it's gonna be spinning in a clockwise direction. And we're gonna put, not gonna do that. We're gonna put that in a cat, okay? Again, because we're doing magic quantum things. We're all physicists now because we use cats, look at that. And then next to that electron, here's the cat for the detector. This is just the detector. And look at that, it's inside a cat. Now we get to make graduate student money. We get to win scholarships and stuff because we're using cats, good. So that detector is gonna connect to a gun. Here's the gun. Again, I have to apologize for my drawing ability. Physicists are not artists, even though they doodle. Okay, good. So there we go. And finally, here's our cat. Okay, just gonna put the ears here so we know it's a cat. Cool. So here's where we're starting, okay? This is at like the second, the moment, the instant before the detector interacts or measures that electron spin, cool? The electron is just sitting there happily spinning away in a clockwise direction. The detector hasn't measured it yet, it's just sitting there. And now let's move time forward by just a tiny second. And now let's let the detector measure the electron. Here's what's gonna happen. We gotta draw out a new little scenario. Now our electron's still spinning in the same direction, but our detector has gone click. So we're just gonna put that little check mark there. So that check mark means that detector is going, all right, detected, the electron is spinning clockwise, so I'm gonna go click. But the detector hasn't yet had time to send its signal to the gun. So the gun's still sitting there and the cat is still sitting there as well. Okay. To continue the story, who wants to guess what happens next? What am I gonna draw next? The electron's still spinning this way, by the way. The detector has gone click, but now what's gonna happen next in our little story here? Yes, hands up person.
Guns don't go off.
So it's gonna send the signal to the gun. Maybe the gun will shoot. I'm hoping it will because I hate cats.
Oh, that's unfortunate. Okay. Well, yes, you're right. The gun will go off, but you need to get a pet because responsibility is the solution
have a
to
dog.
that kind of attitude, sir. Okay, good. Excellent.
I have a dog.
So here's there's another hand up person with a kind of rainbowish background there. Yeah.
The cat was
Yeah, you're way ahead of us. So you guys are both right, and you're right in order. So let's do it one step at a time, right? So the next step is you're absolutely right. Gun goes off, bang, right? But the bullet is now flying through the air. It hasn't reached the cat yet, right? We're telling a story one step at a time. That's what these cats allow us to do. And finally, again, you're both right. We're going to draw out that final scenario. Clockwise. I've noticed the quality of my drawings diminishing over time as I start.
Where the cat falls on the side with a bullet inside.
Yeah, we're not going to get too descriptive, rather, just because I'm not good enough at drawing. But here's what I'll do. I'll meet you halfway here, and we will put little X's there. There we go. There's our cat, okay? So pretty straightforward, right? We told a story using our cats. Now, this is pretty cool because you're already doing what graduate physicists, it takes us like an embarrassing amount of time to learn how to do, is just how to tell stories with these cats. This is a huge part of what physicists are doing with their time. So good. That's how we tell that story. Now, let's compare that. Remember, this whole sequence, right? The electron spinning this way, and then the detector going click. The detector is only going to go click if the electron is spinning clockwise. right? And it's only if the detector goes click that the gun will go off, and only if the gun goes off that the cat will die. So this whole story can only happen this way if this electron starts off spinning clockwise. If the electron's spinning counterclockwise, the story is going to become an awful lot more boring because, yeah, this really is getting pretty bad on the illustration side.
Because the cat will not die, so nothing will happen.
Exactly. Does that make sense to everyone? Like the detector never goes click because the electron is just spinning in the wrong direction, right? So this is the most boring story that we could imagine. In fact, we just end up redrawing the same thing. You know, detector, gun, nothing has happened because the electron is just spinning in the wrong direction. And our cat gets to do great cat things. Okay, so, okay, this is really getting messy. These are all in cats, blah, blah, blah. Okay, great. So 2 different stories, 2 very boring stories. You guys have been very patient so far. Here's where things get a little crazy. Okay, the first story is what happens if the electron is spinning clockwise. The second story is what happens if the electron is spinning counterclockwise. But remember, I started this entire story with the very crazy argument, or I made the very crazy sounding case that electrons can do both things at the same time. So now I'm going to ask what happens, or I'll show you what happens. I'll walk you through this, and at a certain point, I think you'll get the pattern. You'll be able to do the cutting edge physics yourself here. But what happens if we play the exact same story all over again with the electron starting off doing both things at the same time? I know you've got your hand up there. I'm gonna give. I'll just ask you to wait for 1 second because I'll do the first step because there's one more ingredient you guys are missing. But then I will absolutely check in with you because I think you're all very bright. You've been way ahead of me so far. So here we are. This is our electron doing 2 things at once. We're going to lay out everything else, right? The detector is still there. The gun is still there, if poorly drawn. And then the cat is, of course, still there. Okay. So here's the weird thing about physics, about quantum mechanics. This electron is doing 2 things at the same time, and now we turn on this detector and we try to get it to measure the direction of this electron. What the laws of physics actually say is that this detector will split itself into 2 different versions. One of them is going to see the electron spinning clockwise, and that version of the detector will go click. So that's that check mark. But there's also the other electron, or sorry, the other version of that same electron. It's spinning the other way, and the version of the detector that then sees that electron does not click. So see what's happened here is this detector is kind of like split. It's one part of it's gone over here, one part of it's gone over here, and now we have electron, detector, and then electron spinning the other way, and detector seeing the electron spinning the other way. Remember, outside of this, we still have the gun. The gun hasn't gone off yet, okay? And the cat, whoop, okay, no idea what that was about. Okay, sorry, a little buggy there. There we go, all right. Gun here, still there. And then, of course, our cat is still there. Okay, good. Now, I'll follow this through one more step, and then I'll ask you guys to tell me what happens to the cat when all is said and done. The next step, so remember, the gun is no different from the detector. It has to follow the laws of quantum mechanics too. And if the detector gets split when it sees an electron spinning one way and another way at the same time, then the gun is going to get split into 2 versions of itself too. One version is going to see the detector going click, and that version is going to go bang. The other version is going to see the detector just sitting there quietly, and nothing's going to happen. So what we end up with is click, gun goes off. Ooh, that was a pretty nicely drawn gun, if I do say so myself. All right, detector doing nothing, and gun not doing anything in particular, and because, again, we're fancy and we want to make people think we're doing something really complicated, we draw in our little cats. Okay, good. Our cat, of course, is still sitting out here because there hasn't been enough time for the bullet from this gun and the not bullet from this gun to reach and not reach our cat. Language gets really fuzzy here, right? Okay, so million-dollar question. What happens next? Yes, rainbow background.
The cat dies and the cat doesn't die.
Excellent. Okay, so you're doing quantum mechanics. Look at this. All right, so you're on the spot now because you decided to pipe up. So this is now, you're gonna have to do some graduate level quantum mechanics. So you're gonna tell me exactly what I'm gonna draw, okay? What do I draw next?
The gun going
Well, what about our detector here? Did the detector, did that disappear?
The detector.
Good, okay, so okay, good. I draw detector, and what else do I draw in this cat?
Oh, the checkpoint.
There you go, detector went click. What do I draw next here?
The gun.
The gun, good. And what state should the gun be in?
What do you mean what state?
Oh, pardon me?
What do you mean what state?
Oh, I'm sorry. Do I
No.
just draw
I
the
know.
gun? It's okay. It's okay. I'll turn to you in a second. Okay, I promise. Rainbow background. Go rainbow. What does the gun look like though? Has it fired or not fired?
It has.
Excellent. It is fired. Okay, good. Now, what state is the cat in?
He's half dead and he's half not dead.
Okay, so what am I going to draw in this cat here?
One XI and one Y.
Okay, not quite. You're close, but remember, so this is in this whole chunk of the story, the electron was spinning clockwise, the detector went click, the gun went off, so the cat
Is dead.
is dead, right? So we're going to draw our little, unfortunately, KO'd cat. Okay, good. And now, gentleman with the red hair, who's patiently been waiting. Yes. What am I going
It's
to draw
not
here?
red hair. I do not have red hair.
Oh, sorry. It must be the red filter or something.
It's not a red filter. It's just a light.
Okay. Well, then I must be color non-clairvoyant. That's a terrible word. Anyway, whatever I mean. Yes. So what am I drawing here? Electron doing what?
Electron going counterclockwise.
Sweet.
Detector not gun off. Gun not fired. Cat not dead.
Awesome, awesome, awesome. You guys are very, very good. You have your own little physics research team now. Okay, great. Boom, boom. Cat
Yay.
is alive. And there we go. Okay. So here is something very, very strange indeed. Because what the laws of physics, this is what quantum mechanics says is happening in this box. So in 1928, a gentleman called Erwin Schrödinger, if you're German, you probably know how to pronounce that better than I do. But anyway, a guy with a very long name said, look, this is what the laws of quantum mechanics are telling us is happening inside this box. I have a problem with this. Why do I have a problem with this? Well, I can tell you for sure I've never opened a box in my entire life and seen inside like a cat that was dead and alive at the same time, sitting next to a gun that was both fired and not fired, sitting next to a detector that was both clicked and not clicked. I've never seen anything like that in my entire life. And yet you're trying to tell me, sir, you're trying to tell me that the laws of physics say that this is what's going on inside this box. And what's more, this is the insane part, the laws of quantum mechanics are super accurate. They work, I mean, our computers, our iPhones, our iPads, everything you've ever used depends, life or death, on those laws of quantum mechanics. So we know they're right. We know they're right. And yet they tell us something is going on that completely contradicts everything that we have ever seen in our miserable little lives. This is really frustrating, isn't it? If you're a physicist, this just drives you absolutely bonkers. Okay, so here's what happens. in 1928 or around there, I don't know. People start to freak out. I call this the zombie cat problem because we have a cat that's both alive and dead at the same time. And so we have to solve this zombie cat problem. Big fancy quantum mechanics people call this the quantum measurement paradox. They call it a paradox because it's like this weird conflict between what the laws of quantum mechanics say and what we think really should happen. We've never seen this happen in the real world, and yet quantum mechanics says this is happening all the time. So here is the first attempt to solve this problem. The first attempt to explain this was, there was a guy called Niels Bohr, and he comes along and says, okay, hold on a minute. I know that the laws of quantum mechanics say that, yes, you can have a box with the cat alive and dead at the same time, but there must be something special about me, so that when I look inside a box like this is an eye, that's your eye looking inside the box. There's got to be something special then about the act of observing the box, of looking inside, that's going to force nature to choose one outcome. So something special happens. I don't know what. Something magical happens. When I look inside this box, all of a sudden, nature goes, oh no, somebody's looking, quick. Destroy one of these outcomes. Just scratch that out. And then this is what you end up seeing. So just as if by magic, because again, people were really confused. They had no idea how to explain this. Something happens when we look inside the box that all of a sudden just destroys all of these weird simultaneous alive cat, dead cat things. It picks one of those outcomes and it makes that outcome real. And this is called collapse, the collapse of a quantum state. So you have this idea that before the collapse, this cat was both alive and dead at the same time, but then it collapses into just one because you looked at it. That was the first attempt at solving this problem. I'm going to pause here because Rainbow Background, who just grabbed a bite out of a cookie, I'm sorry, had his hand up a minute ago. Please go ahead. You can swallow if you want. You don't have to.
Why didn't the dead cat stay?
Why didn't the dead cat stay? That's the $1 million question. So that's actually a really, really good question.
I would have liked that, Mac.
Pardon me?
I would have liked what Mac just said.
Oh, I see. Yeah, well, right. But let's assume, though, that we're not psychotic and we don't want the cat to die. Let's just ask the basic question, though. Sorry, did you say Mac?
Psychotic?
Oh, yeah, let's not worry about let's not worry about that.
Mac.
But Mac. Okay, Mac. So Mac just asked the exact same question, essentially, that Albert Einstein asked at the time. Albert Einstein did not like this one bit. You may have heard of Albert Einstein. He's like, when somebody seems like they're really smart, people say, oh, well, what are you, an Einstein? He's that famous. He's literally so famous that people reach for his name when they think of like the example of what a really smart person would say. Albert Einstein looked at this and he said, I have a problem with this. You're telling me that you just magically destroy just by looking at the inside of the box? There's something about you. Why are you so special? What's the big deal there? How are you, you're magically but yes, so Mac, that is exactly what Niels Bohr was saying. He was saying there's something basically magical about the act of looking at one of these kind of weird simultaneous alive dead situations that forces the universe to pick one and lock that one in. Now, I'm like Mac. I'm not like Einstein. I wish I were, but I certainly agree with him on this, that this seems a little crazy. This seems a little implausible. But here's the thing. In 1928, there weren't really any alternatives. People were really jittery and nervous because this was the only solution that anyone had to what seemed like a really, really serious problem. And it stayed that way until about 1953, when someone came up with a very dangerous and very radical idea. Here is our box. You're going to have to be patient with me while I draw out terrible little doodles. Okay. So in 1953, there was someone called Hugh Everett III who was really, really smart and almost bald and really liked to eat fast food. and who I think might have worked on like the Manhattan. I don't think he worked on the Manhattan, but anyway, he has some weird connection to it. Anyway, bottom line is, here's our dead cat. Okay, good. Here's our live cat. And here's what Hugh Everett III said. Hugh Everett III said, listen, you think you're really special. You think you have this special collapse power where you can force nature to just pick one of these two situations and make it happen. I've got some news for you. You're actually not special at all. In fact, I can just draw a picture of you, and if I stop pretending that you're some special magical thing, then you're just like all the other things in the universe. I can put you in a cat. This is you with apparently a really long Y tail. That's you. Okay, why would this matter? Well, if you imagine, all of a sudden we've now we've taken all our hubris, all of our assumptions, the assumptions that we're special out of the equation. We said, you know what, I give up. I'm just going to say that I'm not special at all, that I'm a quantum thing just like the cat, just like the gun, just like the detector, just like the electron. I'm no different. I'm made of atoms too, right? So I should be able to put myself in a cat like this. Now, here's the thing. If I then look inside the box, what's going to happen to me? Any guesses? I gotta pick one. Lex, was it Lex? Yeah, go ahead, Lex.
He's gonna die.
Well, he's just looking inside, right? So all he's doing is open this box, and he's gonna look inside.
The cat's gonna bite him. The cat's gonna bite him.
Okay, not quite. Mac, yes, go ahead.
Oh, the cat's gonna be alive.
He's going to see the dead cat.
He's gonna see the dead cat. Oh, interesting. Okay, so let's replay this. I wanna kind of go back here and show you the story. So remember what happened when, for example, we started off with our electron up here, right? It was spinning in both directions at the same time. The detector decided to look at the electron. What happened to the detector? Well, the detector got split into two versions of itself, right? One version went click, the other didn't. Then the gun got the signal from the detector and didn't. It got split into two versions of itself. One went off, one didn't. And then the cat. It got split into two versions of itself. One lived and one died. And now you are going to look inside the box, and what's going to happen to you?
You're going to die.
Oh, sorry, some feedback there. What if you're no different from the cat or the gun?
You're going to die because the cat died.
Well, all you're going to do is look inside, right? There's no gun pointing at you or anything like that, right?
Mac, please turn off your mic. It really hurts my ears. Or will.
I think there's a little bit of feedback, yeah. But okay, so I'm going to draw this out for you, and I think once you guys see this, you'll be like, oh, of course. Here's what's going to happen. All the same rules apply to you, which means that just like the detector, the gun, the cat, you are going to get split into two versions of yourself. One version is going to see...
Is going to see the dead cat. One is going to see the alive cat.
Oh, sorry, I shouldn't put a smile on that unless that person is actually Lex. This is a sad experimenter because the experimenter likes cats, okay? Yes, one version of this experimenter sees the dead cat. The other version, and now you're gonna have to be patient with me because I am incredibly slow, and that creates a really awkward pause in the explanation as I have to fill time with words that don't really mean anything. And then we get to the point where, there we go. Okay, the other version sees a living cat, right? So all of this—
It should be sad.
all of this comes from the fact that we stopped assuming that we were special. We said, you know what? The same laws that apply to every other thing in the universe, that apply to detectors, that apply to guns, that apply to cats, that apply to electrons, those same rules should apply to us. Because you know what? We're made of electrons and atoms and stuff that does stuff like this. Now, here's what happens. If you ask this experimenter, you look at these two different versions of the experimenter, and you ask them, how many versions of the cat did you see when you opened the box? Well, this experimenter is going to tell you, I just saw one. I mean, obviously, I just saw one. The cat was dead. It's a really sad day for me. And I'll tell you what else. I've never seen anything be in two states at once in my entire life. And if you ask this version of the experimenter, what did you see? They'll say, I only saw one outcome. I saw the cat that was alive. There's no other cat. There's just one version of it. In other words, from the experimenter's standpoint, it will seem as though the cat collapsed. It'll seem as though the cat was only ever in one state. But it's actually an illusion. It's because the experimenter is trapped now in one of these two timelines, in one of these two stories, and they can't see the other version of themselves in the other one. Okay. Questions? Lex, it sounds like you're curious or struggling to absorb.
I'm on both. I'm curious why there can't be two forms of me, one asleep, one here.
Well, actually, that's kind of what this says, right? That really every time we encounter a thing that's doing one thing, and that's also doing a second thing, anytime you run into anything like this, you're going to get split into two versions of yourself. So literally every time the universe, and this happens all the time. I mean, the laws of quantum mechanics say most things are in a state like that. And so anytime you look at a thing,
Thing one, thing two.
Thing one, thing two, there you go. Yeah, that's right. I gotta hope that I'm not infringing on copyright with that. That's right, yeah. Anytime you encounter something like that, you get split into as many versions of yourself as there were things that you looked at here. And so this is this picture now of a really weird universe where there are versions of us running around doing every possible thing that the laws of physics say is possible, and we're trapped in just one of those because we're one of these experimenters. We're just one version of ourselves, and we only ever see one outcome. We think that's all there is to the universe, when in reality, it's a much, much bigger, much stranger place because these things are happening all over the place. I'm going to pause there and just ask if there are any questions in general about this stuff. Yes, Matt?
If the humans were in the box, would the humans die?
I mean, if the human was, let's say, there we go. If the human was in the place of the cat facing the gun, like if this wasn't a cat and it was a person, yikes. Yeah, then you would have a human that was, I guess, half dead and half alive. One version of the human would be dead, the other would be alive, according to this idea. Yeah.
Who created the idea of quantum mechanics?
Okay, what a great question. It's actually there are a number of people who contributed to it, but this is an irresistible opportunity to talk about. I literally prepared a slide or a set of slides just in case someone asked that very brilliant question.
Yeah, but if someone created it, now how do we know quantum mechanics is true?
Very good question. So quantum mechanics, apart from saying that there are weird parallel universes and all kinds of strange things that are happening around us, quantum mechanics makes a lot of other predictions. And those predictions are incredibly accurate. As far as we can tell, quantum mechanics is the single best, it is the single best theory of anything we've ever come up with. It can predict, for example, how a number called the charge to mass ratio of the electron. So this electron spins around, it weighs a certain amount, and it also has a certain charge, doesn't matter what that is. Bottom line is it can predict the charge to mass ratio of an electron down to like a ridiculous number of digits. It gets it super, super accurate. And the laws of quantum mechanics are what we rely on to make computers, to make iPhones. So literally right now, we're communicating via Zoom, which would not work if our understanding of the laws of quantum mechanics were wrong. So we have a very high degree of confidence that they're right. And one of the key questions might be, and maybe I can read into your question something a little deeper as well, which is like, how do we know that electrons, for example, can do two things at once? How do we know that different stuff in the universe can be doing multiple things at the same time? And we can look at that here with this kind of Thomas Young, this couple of slides I was going to share, but I want to make sure I answered your question fully. Do you have any? Does that make sense?
Yes.
Yes-ish? Okay.
Yes.
All right. Excellent. So I want to introduce y'all to Thomas Young. Thomas Young is the smartest person you've never heard of. He was a doctor. He deciphered super famous ancient texts. There's an ancient text called the Rosetta Stone, and he's the dude who deciphered it. He was an Egyptologist, which means he studied Egypt. He was a musician. He had a lot of funny looking shirts because he lived in the 1800s. And he's known as the last man who knew everything. So one of the things I remember thinking about back in the day was like, there's a lot of stuff to know now. You gotta know math and computers and chemistry and English and whatever. There's a ton of stuff that people know today. And that's because we've piled knowledge on top of knowledge for hundreds and hundreds of years. But there probably was a person at some point in time who was the last person to know basically everything that people knew about math and physics and Egypt and music and all this stuff. And with some exaggeration, that person was Thomas Young. So Thomas Young is known for just knowing a whole heck of a lot of things. And one day, possibly because he was under quarantine, not necessarily because of COVID-19, he decided that he would just go about discovering quantum mechanics. So he's sitting at home. He's like, I'm bored. I want to do something interesting. And he says, I'll run an experiment. Here's what he does. He takes a big beam of light. So sunlight just coming in through the window. And he does some fancy stuff to it that you don't need to worry about. But basically, there's a big beam of light. And then he puts up a screen. Okay, the screen. And he's going to poke a little hole, a tiny little hole into that screen so that the big beam of light kind of overlaps on top of that hole. So some chunk of that beam of light is on top of that hole. And then he's going to put what he calls a viewing screen far from the hole. So now, this is going to be the most boring result you'll ever see. Surprise, surprise, he gets a bright spot. Okay, so there's a hole in the screen here. There's a beam of light hitting that hole, and the little part of that beam of light that makes it through reaches the screen, and boom, you get a bright spot. Nothing too exciting there. Thomas Young says, all right, I'm going to try to poke another hole in the screen, a different tiny hole. And surprise, surprise, excuse me, he gets a different bright spot. Nothing too shocking so far. Here's a question. I wish I had a slide in between. Let me just take this out and pretend that you did not see it. Look away, look away. All right, there we go. Now he pokes two holes into that screen. What do you think is going to come out the other side? Yes, rainbow.
Two holes. Two holes.
Two bright spots, right? Most people would say, all right, there's going to be a left spot and a right spot. Like, what do you want from me? This is a pretty simple experiment. And this is where the insanity comes in. This is actually not what happens. This is not what happens. Mind-blowingly, oh, I should have put that up because that's like the perfect graphic for this. Mind-blowingly, this is not what occurs, not what occurs. Instead, here's what he saw. Boop. Whoa. What is this weird looking stuff? That's the thought process he went through. I really should be seeing two big blotches. I should be seeing two bright spots. I'm not. What's going on? When I covered one of these slits, I had one blotch. When I covered the other one, I had a different blotch. And then I uncover both, and I get this weird looking mess of stuff. That makes no sense to me. That seems insane. And this is, well, yes, what, why though? Okay, so this is the big mystery that Thomas Young solved, basically, or at least the effect that he explained. Here's how he explained it. If I have something on the screen here that's more complicated than like the sum of each of these independent things. So basically like, oh, this is a terrible way to explain it. Basically, if I have something really simple that comes out of hole 1, something really simple that comes out of hole 2, just one blotch, but then I open both and I get something really weird, the only way that's possible is if there's some weird mixing effect going on. Like it's almost like the light from hole 2 is like mixing with the light from hole 1 to create something that's even more complicated. They're like overlapping in weird ways, maybe. They're mixing together. It's almost like, you know, if you have a heap of baking soda and you have a glass of vinegar, you guys might know, right? You mix baking soda and vinegar together and you get a fuzzy mess, right? Okay, so if you didn't know that baking soda and vinegar have a very special kind of weird mixing process that goes on, you might just think that if I mix baking soda and vinegar together, I should just get like this wet heap of baking soda. It shouldn't look like anything special. But something more is happening. You're getting a fuzzy mix, and that mix is your hint that there's an interesting, in this case, chemical reaction, or the whole is bigger than the sum of its parts. Yes, Rainbow.
That because the vinegar is acid.
Yeah, that's right. In that case, it's because there's a special kind of chemical mixing process, and you get something, that's right, you get something weirder, right? Something that you wouldn't have expected. And that's exactly what's going on here. Hole 2 is like the baking soda and hole 1 is like the vinegar, and you're kind of mixing them together, and whoa, you're getting something that does not look like just a wet heap of baking soda. You're getting something that's a weird, more complicated thing than you ever imagined. And so there must be, this is what Thomas Young said, there's got to be some interesting mixing effect going on. Okay, light from slit 1 must be mixing with light from slit 2. And for a while, everyone was happy with that. Until somebody realized, well, wait a minute. If I take this beam of light and I tone down the beam, I reduce the beam to the point where, now I should mention, light actually is made up of tiny little particles. Okay? Tiny little particles, just like all stuff in the universe is made up of atoms. So what Young was thinking was like, hey, maybe those particles are kind of mixing, they're bumping into each other and doing interesting things that leads to this pattern. But if that's true, then if we tone down this beam to the point where there's just one light particle going through at a time, then there's no way that light from hole 1 could be mixing with light from hole 2 because there's only one particle of light going through at a time. And so if we do that, if we have just one particle of light going through at a time, we should go back to just seeing our blotches, our 2 bright spots. What's incredible is that that didn't happen. Even with one particle of light going through at the same time, you still get this weird looking pattern. So it's almost as if that particle is mixing with itself. I mean, some part of it is almost like going through hole 1 and hole 2 at the same time. And that was actually the first hint that stuff in the universe could do this weird gymnastics, could go through one slit and another slit at the same time, could spin in 2 directions at once, and so on. So, I mean, this last bit is a little bit, I think, a little bit more confusing, perhaps more advanced. If you don't get that, totally fine. The main upshot of today's conversation is hopefully this take home here with the whole, hey, there are multiple versions of you running around in the universe. And I think that's my story. Does anybody have questions about any of this stuff or any other stuff? Yes, Rainbow.
Why did you want to learn about quantum mechanics?
Why did I want to learn about quantum mechanics? Well, I guess I started off, I wanted to become a chemist. I wanted to do chemistry. And I kept asking questions that annoyed my teachers and professors about why different chemicals were interacting the way they were. So basically what happens is if you go to university or you go to high school, at some point, your teacher's going to tell you, yeah, you mix baking soda and vinegar together, and then they kind of do this weird thing. And then you go, okay, why do they do that weird thing? And then they go, I don't know, maybe ask like somebody who does physics. And then you go, oh, wait, why don't I just go and do that? And then, so you go do that. And that's what happened to me. So basically, I asked too many questions about baking soda and vinegar.
Didn't you eventually figure it out?
Well, actually, I'm lucky because people like Schrödinger and Thomas Young and a ton more people actually figured it out for me. So I got to just like read their thinking and then, you know, eventually kind of hopefully come to some kind of understanding about it. But, oh, sorry?
Did anyone tell you?
Yeah, so they're you know, teachers and profs who teach physics and stuff. And they all taught me this stuff. Yeah. So it's not actually, you know, I think one of the big take homes here is people think that one of the things I've heard a lot is people say, oh, I don't like math. I'm not good at math, this and that. Math actually is a lot simpler than most people think. I think the key is not to be scared of making mistakes and to just dive into it, because very quick, like here's the payoff, right? The payoff, the moment you understand math, the moment you understand physics, like you can understand how crazy the universe actually is. And you can start building your own sort of theories and building on top of this sort of thing. But you can start to like decipher weird things that, you know, there's so many deep questions about, you know, whether collapse is true, whether collapse happens, or whether parallel universes are true. If collapse happens, like, you know, the role of, some people say consciousness could be involved in that. Anyway, it gets really crazy. But to get to the point where you have those interesting discussions, you just need to cover a little bit of math. So, I mean, I think I'm biased, but I think it's totally worth it.
What gave you the idea of baking soda and vinegar?
Oh, pardon me?
What gave you the idea of mixing baking soda and vinegar?
What gave me the idea of mixing baking soda and vinegar? Oh, it's not my idea. So I had a, I don't know, I had a teacher, let me see, I can't remember when, but you know, when I was in like grade 2 or something, and it's this very common, very fun experiment you guys should totally do. And I apologize in advance to your parents for the mess that you're going to cause them to make. But if you go out and just have, you know, some baking soda, some vinegar, you mix them together, something cool will happen. A teacher of mine once showed me that. And I guess I just remember that now. So.
Jeremy, one time we actually used that to unclog my sink.
Oh yeah, that's true. Yeah, so there you go. So baking soda and vinegar isn't just useful for making messes. Yes.
Wait, 380 liters? No liters of baking soda with a liter of vinegar.
Oh, I'm sorry. I'm just having a little bit of a hard time hearing you. Do you mind repeating that?
Once I mixed lots of baking soda and lots of vinegar.
Hey, yikes. Well, yeah, your parents will be really happy with you for doing that too. Actually, as long as you're mixing it in like the toilet or something, at least you'll get some cleaning out of it. Awesome. Good to know you guys are all a bunch of experimentalists too. So any, I don't know, do you guys have any other questions about, I mean, there's so much we covered, but baking soda and vinegar questions are fine too.
Jeremy, could we finish the slide?
Oh, yes, actually. So I believe I finished the slides here. Yeah, because the rest of it was, I was thinking of just taking you guys through kets and stuff, but we did that using this. I just wasn't sure if it was going to work. So I set up some emergency slides just in case. So yeah, we are through them.